Before we get to this kind of trap things, I have to finish what I started last time, which is this description of the complexity of spherical spin glasses. So I gave you last time an interesting picture for the case of pure P spins, and which was, if you remember, compatible with the view that for pure P spin, and we know that, in fact, for pure P spins, spherical, at low temperature, we have one-step replica symmetry breaking. Okay, which, as you know, we don't know, and is not even completely true, not supposed to be true for pure P spins on the cube. All right, so let me summarize what we had. We had this picture of complexity where we had an exponential number of local minima. We could compute the exact constant, which I call the complexity, the mean number of local minima. And same thing with critical points of index 1, 2, 3, etc. And we could also, in fact, compute the number of critical points of index k in an energy band of critical values in a given energy band. So we could, and we have seen the main lesson is that there is a very strong relation between the index and the value. That's pretty surprising. So if you take an index like local minimum, index 0, then all the local minima are in a band of energy which is at the very bottom of the landscape. The critical points of index 1 are in a band which has the same upper bound, which I call negative E infinity, and a higher lower bound, and etc. So you have this kind of hierarchical structure of the bottom of the landscape. This hierarchical structure of the bottom of the landscape imposes that when you want to go from one minimum to another minimum, deep minimum, then you have to climb an energy barrier which is diverging with n, right? Because you have to find a critical point of index 1 at least. And so you have to climb a large energy barrier, which means that the time to go from one minimum to another minimum has to be exponential in n. So this begins to look like the kind of trap model that Alex was just describing. If you have, imagine, and nothing is one-dimensional here. We're on a very large dimension. You have a local minimum and maybe a valley around it. Remember, we have this function, which is a smooth function on the sphere. Now you should think of the sphere in very high dimension. So you have one region which is very low. You have another one, and in order to go from one to the next, you have to climb higher, right? So these regions play the role of traps. So you could imagine that the motion in those traps, in this field of traps, should look like what Alex is describing. This has not been proven, right? And this is hard to prove, because in order to prove it, but I conjecture it's true. And I can even give, and the kind of law of the arcsine law that Alex described for this very, very simple model in dimension 1 should also be true there, once you write it with a proper normalization. This is an interesting conjecture, extremely difficult, for the following reason. The information I gave you, it tells you something about the depths of the traps, the depths of the valleys, about the index of the critical points, but doesn't tell you much, in fact, about the position of these traps on the sphere. And more importantly, doesn't tell you much about what topologists would call the Witten complex. That is, when you take one minimum and another minimum, you look at one path going from one to the next. How high does it have to climb, really? You know, it has to climb a certain amount, which is proportional to n, but how much, we don't know. So we need to know all those paths between different local minima. And this kind of information is not available yet, right? So the way we got these results on the complexity does not allow us to get this whole geometric picture of where the traps are and how are they related, and how high do you really have to climb between two paths. And so for the conjecture I just mentioned to be valid, you need the following type of information. You need, in fact, to know that when you climb from one trap to get to another one, from one deep well to go to another one, essentially you have to climb to the typical values, to climb to the bulk of the sphere, to just completely lose the information of where you started from. And then if you completely lose this information, you have this kind of renewal structure which will make things look a little independent, even though they are very correlated, like in Alex's model. I still believe this is true, but it could take a long, long while before we can prove it. All right, so that was just to make the link with this. So we had this formula, this picture, and I said also something else last time. I said that with this formula, you could find, with this complexity picture, we could find the ground state. The ground state was exactly where the complexity vanished, right? This is very interesting and not obvious at all. It looks like, sure, but in fact, it's really hard. In order to prove it, we used the Parisi formula, and we used the information that we knew that there was one-step replica symmetry breaking. So here is a very good problem if somebody wants to have one. In fact, it's a very bad problem because it's hard, but an interesting problem. What we did here was compute the log of the mean number of minima, say. What would be really interesting would be to compute the mean of the log of minima, right? So invert the mean and the log. So go from an annealed thing to a quenched thing. This is really difficult, but I believe that in the pure case that I described, it should be true, that the quenched asymptotics should be the same as the annealed. That is, what I described here were the asymptotics of the mean number. I think you can forget the word mean here. You take the number of local minima. It should behave with the same exponential behavior. But so for that, what you would need to do first is to control maybe the second moment. Control the concentration around the mean. Right? If we could do that, so the second moment, obviously you would have to have some kind of modified second moment method. If we could do that, and if we could prove a priori that the number concentrates around its mean, then we would not need the Parisi formula. This would be a proof of the Parisi formula at zero temperature, which doesn't mean much, but this is what we're doing here is at zero temperature, and this would be totally independent of the Parisi formula that we have seen before. All right? So there is a large impact at being able to do this concentration. And we haven't been able to do it. So when I say it's hard, we've tried this with Tuka and Tuka-Finger and did not really succeed yet. But that would be very interesting. It's a hard problem because in some in some non-pure spin glass cases, what I'm saying will be wrong. The concentration will not happen. So let me explain that now. So I'm taking again my spherical, I won't write that again. I have my spherical mixed p-spin model. As before, so you remember my Hamiltonian is sum of beta p h and p. And and sigma is here in the sphere of radius square root of n. Okay, so what I described last time was the case where it was pure. I described the case of h and p. Okay, and so again now, so this is a smooth function when the beta p decays fast. This is a smooth function in the sphere, and it's so hn should be looked at. It's a smooth, in fact, Morse function on the sphere. So we can count. I look at it like this: a smooth random Morse function on the sphere. And so I want to look at, again, I want to compute the following. The expectation of the number of critical points of index k below a level u. So remember what that is. This is the number of critical points, or critical values, in fact. The number of sigmas in the sphere such that hn is, so the gradient of hn at sigma is 0, which means sigma is critical, such that the index of the Hessian, the second derivative, if you want, of hn at sigma is k, and such that the value of Hn is below nu. Okay, so I look at, this is this thing, and I want to compute the mean of this. And remember what I said, in fact, what will prove the theorem is, that is proved by, in this generality here by Tuka and myself, you can find on the archive. And so this A is for Aufinger, I should write this. The result I presented last time was the result joint with Aufinger and Jiří. So in this general case here, we also have a result of the same nature. The limit of 1 over n log of this mean of critical number of critical points of index k below level nu. This limit exists, and we call it theta k of u. And theta k is explicit. It's given by a variational problem that I don't want to, I mean, it's a long formula. It's computable explicitly given by, so it's given by a variational problem in 2 variable. So it's not too hard. It's not like the Parisi formula. It's in 2 dimensions. And this problem is parametrized by only 2 things. By 2 numbers, which are nu prime. Remember, that was nu prime of 1, and nu second. 2 numbers, which are nu prime of 1 and nu second of 1. Okay? So this thing is explicit, and the picture is a little, and you have 2 classes that come from this. One that I call the pure-like case, which will look, of course, like the pure case that we had before. And we understand this, even though we cannot prove that, this corresponds to the 1 RSB situation. So the one-step replica symmetry breaking at low temperature. What we describe here, of course, is at 0 temperature, but that's the shadow of this, right? So in this case, it's really it looks like what we had before. So you would have a curve like this. And so you would have a threshold, which I call negative infinity here. So if I draw theta 0, again, the complexity of minima, remember, k equals 0 corresponds to minima, I would have something like this. So this really looks like what we had before. You have this threshold E0 here. But if now there is a little difference between the pure-like and the pure case, that there is, if I try to draw theta 1 now, you have this kind of fan structure, but it starts here instead of starting there. So you have here again the threshold negative E1. But this thing here is not the same as that. These 2 points here are different, so E infinity is different from the E prime infinity if and only if the model is not, or equal rather, if and only if the model is pure, right, as we described before. So as soon as the model is not pure, you have this new region here. So what is this? And same thing then for theta 2. So this would be theta 0, this would be theta 1, this would be theta 2, etc. And these thresholds converge to here. So what does that mean? This structure is very similar to what we had before if you look at the deepest point. All the local minima are between these 2 things. Maybe if I want to keep the same notation that before, I should put them like this. So all the local minima are between negative E0. This doesn't work, right? Does it? Oh, deeper? Does that work? Good. All right, so all the local minima are between negative E0, NE0 and negative NE infinity. So this is very deep again. So the local minima are all between negative NE0, negative NE infinity, as before. It still doesn't work, right? It works? Good. All the critical points of index 1 are all in this region here, etc. All the critical points of finite index are in this region. In fact, all critical points of finite index are below this thing. So that's as before. Now, what is this new region? This is the new interesting region. In this region, you see, so here in this region, the number of local minima dominates. You have many more, because theta 0 larger than theta 1 means that the exponentially the number of local minimum dominates. It's much larger than the number of critical points. But here, the number of minima does not dominate, at least in the exponential scale. You have essentially, they grow together. The critical points of index 1, 2, 3, and minima are essentially all the same in the exponential scale. But they still grow. This curve's growing means, oh, I'm sorry, this was, I should keep it like this. They are here, in this region. Because here this function growing means that there are critical points, there are minima in this region. So that did not exist before. So in this region here, how can one picture this? Before, at least I see this region here, as a region made of wells. Because again, you have many, many more minima than you have critical points at any given level, which means that you have to climb pretty high if you want to go from one deep well to another deep well. Whereas here, in this region, you have the same number. So you don't have this phenomenon of barriers. So this is a region where you have energy barriers between deep states. And here, a priori, you don't have to have them. Maybe you do, but at least this is not imposed entropically by the number of points. So here, I believe that there are no energy barriers. So here in this region, I see this as very, very shallow traps. All right? Now, so here is a big conjecture, which we do not know how to prove. The ground state is here. All right, conjecture, the ground state. So the ground state, remember, the minimum, you divide, the limit of the ground state, which is the minimum divided by n, is negative E0. So we can prove that in the pure case, but in this pure-like case, we can't. Why? Because we could not control, again, the concentration. If we could control the concentration, it would be obvious. What is clear is that this guy, let me call this ground state infinities. This is the limit of the ground state. It's clear that it's, in fact, proven that this thing exists, the limit exists, and that it is larger than negative E0. That's just the Markov property. It has to be on the right of this. But proving that it's here, you need to control the concentration, and we can't do it. Or you would need to know that in this case, you have one-step replica symmetry breaking at positive temperature, so that you could apply the Parisi formula, compute the free energy, and let the temperature go to 0. And we do not know that. Okay? So the conjecture here, that's one conjecture. Related to this conjecture is, in this class, at low temperature, you have one-step replica. So something related to that, at low temperature in this class, you have one-step replica symmetry breaking. Remember what that means? In the Parisi formula, it means that the functional order parameter, zeta, as I called it, is made of two atoms. All right? And that we don't know. So let me give a name to this value here. We call it G of nu prime and nu second in our paper. So this number here is strictly positive. That's the value at which the complexity saturates here. Oh, I'm sorry, not this one. This one. Not where it's saturated, but where this forking here begins. Okay, so that's the first class. Now there's a second class, which we call the full-like class. And we believe that this corresponds at low temperature to full replica symmetry breaking. But we don't know that. So the picture of complexity is different now. It looks very similar, but it's like this. And then this. So it's just this region now, if you want, has grown. This G is now the place where this fan structure happened is now negative. Okay? So it's the same thing, except that here the horizontal axis is here, and now I move it there. Right? Very simple. So there's one parameter, which is just this G, which is here negative. So now, what is this structure? Why do we believe that this is very different? So here you have also this negative E infinity. And here you have this negative E0, but which is also the same as negative E1, etc. Because this curve here in this region is the same for theta 0, theta 1, theta 2, etc. So what does that mean? When the complexity is positive, so you have an exponential number of local minima, an exponential number of critical points, but you have the same exponential number. They differ only when they are very rare, right? Because in this region, remember what that means. It means theta is negative, so the complexity is negative, which means that the number is exponentially small. The mean number is exponentially small. So you see the difference between the minima and critical points only when they don't matter. When they do matter, they are all the same. So in this region, again, there is no reason to have any barriers between states. Right? That's completely different. And so in this regime here, we can prove that the concentration does not happen. We can prove in this regime that the ground state is strictly larger than negative E0. So you have the ground state is somewhere here. So what does that mean? Take an energy here. Okay, take this energy negative U. Right. What does that mean? The complexity here is positive. Right? Which means that at this level, below this level, you have an exponentially large mean number of minima. The mean number of minima below this is exponentially large. But the probability that there exists one is in fact tending to 0. Because the absolute minimum is here. So in fact you have no local minimum here. Right? So what does that mean for those who are not used to dealing with strange random variable like that? If you look at the number of local minima, it's a random variable with integer values. Its mean at this level, its mean is huge, but the probability that it is 0 is very close to 1. Right? That's perfectly possible. All right? So what does that mean? That means that there is a tiny probability, a very rare event. So most of the time this number is 0. And there is a very rare event where this number is huge, might even be much bigger than exponential. Okay? So this, of course, is a random variable which does not concentrate. Computing the mean doesn't tell you much. So that's why I was saying that proving the concentration here, in this class, concentration will not be true. In this class, it will. All right? I mean, it will. I conjecture it will. All right? So this class is much more interesting, and this class, for me, corresponds to the full replica symmetry breaking. Okay. In this class, probably also, here's what's happening. The picture that Alex showed of trap models is completely irrelevant here, because you don't have traps. Here you come from the bulk in energy down, and you maybe you don't cross energy barriers. The energy barriers that you cross are not diverging with n, or very slowly. So essentially you get to the bottom, to the ground state, in essentially finite time. Maybe time diverging with n like a polynomial, but certainly not exponential. And you are not trapped. Okay? You just go there by just crossing small barriers. So I will explain that maybe. And we understand this type of dynamics. It's called the Cogliandolo-Courant dynamics, and we've established with Alice Guillonnet and Amir Dembo some time ago that the limit is correct. So now the problem would be to study these limiting dynamics in large time. Okay? It's clear that in this class, the Cogliandolo-Courant dynamics that I will introduce later cannot work down to equilibrium. They have to stop here. As soon as you have traps, the time scales that you need will be diverging with n, and so the order of the limits that are taken for the usual dynamics are not true. Right? So this is important. Another way to have guessed, maybe, we could have guessed that concentration could not work here. And it's here, is the following thing. The whole picture I'm giving here depends only on two parameters, the derivative of nu prime at 1 and the second derivative of nu prime at 1. So this picture of complexity depends on two parameters. So it means that if I had taken two different nus, two different set of beta p's, two models, which have the same nu prime of 1 and nu second of 1, then they have the same complexity picture. That may sound bizarre, because a priori two models, I mean, nu plays a big role. But it's not bizarre here if you believe that you have one RSB, because now we can count the parameters. If you believe that you have one RSB at low temperature, then everything is determined by the order parameter, and the order parameter is the distribution of the overlap. It has two atoms. An overlap with two atoms is in fact determined. You need to know, and one atom is fixed, so the only thing you need to know is the position of the other atom and the mass, two parameters. Right? And they're in fact in one-to-one correspondence with these two parameters here. So that should be okay. But here, in this context, the full light class, if you don't have one-step replica symmetry breaking, even if you had two-step replica symmetry breaking, which we don't expect to happen here, then you don't have enough parameters there. So in this case, this means that the annealed picture that we have provided here will not be enough. Right? It will not be enough. We need to take this expectation outside of the log. And the mean will not predict much. Okay, and that we don't know how to do. All right, so what I didn't say is how we get all these results. But since I gave a series of lectures here some time ago explaining that, I will just pass on that and send you to the papers. What is really interesting is that, in fact, we obtained this by an exact formula linking this problem to a problem about random matrices. And a priori, there are no random matrices here. And the whole information we have here, all this comes from information on random matrices. So just in order to give a hint of why is there a random matrix in this problem? And what are the tools? So the tool to study such a thing, when you want to forget the index k for a moment, you want to compute, say, the number of critical points. So you are trying to compute the number of points where a Gaussian random function vanishes, right? Because being critical means that the gradient vanishes. Okay, there is a general formula for that, which is called the Katz-Rice formula. If I give you a Gaussian smooth function, how many zeros you can compute by the Katz-Rice formula. Okay, so it's there. That's purely a Gaussian tool. And purely something that you can use on smooth structure. We cannot use the Katz-Rice formula really for the cubic case. Now, when you apply this formula, you have to compute the law of the Hessian. Because you have to compute the law of the derivative of your function. So the derivative of the gradient is the Hessian. But you can do that. You know the law of H, so you can compute easily the law of the triple H, gradient, and Hessian. This is a Gaussian computation. If you know the law of a Gaussian function, you can compute the law of its derivative and its second derivative. So it's easy to compute this joint law. It's a huge Gaussian joint law. Once you have this, because everything's Gaussian, you can easily compute the law of one of the components, here the Hessian, conditioned on the others. So you can compute the law of the Hessian conditioned on the fact that the point is critical. You can compute the law of the Hessian conditioned on the fact that the point is critical. And when you do that, so what kind of law can the Hessian have? The Hessian is a matrix. If you look at it in local coordinates, it's a matrix of size n-1 by n-1, because the sphere has dimension n-1, which is real and symmetric. Okay? And it's random, of course. And it has, so you have a random real symmetric matrix, large. Obviously, on top of that, this distribution at a critical point, so when you condition by the fact that the point is critical, is invariant by the orthogonal group. The whole model is. So I have a random matrix of size n, or n-1 by n-1, real symmetric, and whose distribution is invariant by rotation. It does not imply at all that it's the GOE. You have plenty of other models. But what we prove here is that in fact it has the distribution of the Gaussian orthogonal ensemble, shifted by a constant which depends on the value of the energy itself. So essentially that's the link. The Hessian at a point, when you condition the point to be critical, is a simple avatar, a simple transform of the GOE. GOE meaning Gaussian orthogonal ensemble, and for those who don't know what it is, it's simply a real symmetric matrix whose entries are above the diagonal, say, are Gaussian independent. For these matrices, we know everything. And so we can compute a lot of things, and this is what we do here. All right? So here, this class, of course, we can't say much. But let me say one thing that I'll be very quick about that, which seems to justify what I'm saying here. Instead of computing the complexity, what we can also compute, or on top of computing the complexity, what we can compute is the following. It's the mean Euler characteristic of the level set. Right? So you fix a U, you look at the region of the sphere where the energy is below that level, and you compute its Euler characteristic. So maybe you don't know what that is, but it's a topological invariant. Okay, you compute this. And so it's a random number, because the region is random. So you compute the mean of this random number. All right? So, and so we can compute that extremely precisely, again using random matrix theory. Here, of course, again, let's take an energy level here. Clearly, at this level, or anyone here, you have the number of minima dominates. It's exponentially larger than the number of critical points. So essentially, it's reasonable to think that the level set below a level U, which would be this bar here, will be made of small regions around those very many local minima, small cells. Okay? if that is the case, then the Euler characteristic of this thing, if you think of it as a union of an exponentially large number of cells, wells if you want, then the Euler characteristic will be essentially exponentially large. You can forget everything else. It's just a union. The topology here is simple. You have a very large number of connected components, exponential, and for each of them, the Euler characteristic will be a number. You just add them, and so you have an exponential number, exponentially large Euler characteristic, right? So this is what you can prove here. But in this region here, or more importantly here, in this region, which is close to the ground state, what you find is that the Euler characteristic behaves completely differently. It is, if you take a given energy level, the mean Euler characteristic will be exponentially large, exponential constant n, the constant being given by this theta 0, of course. And you move the energy level just a little bit, and it will become negative exponential n. So it oscillates widely, in fact, with the sine function, between an exponentially large number and negative an exponentially large number. Okay, so it's completely different behavior. This behavior is essentially this. You see, in one region you want to see a sea of wells, and that's you have a sea of small connected components. And negative exponential n means that the complement of this is like this. So the topology is completely different. Right? That's the only indication we have that these things are really widely different. Here, all right, so I'll stop with this. We could go on for a long, long time. And I don't want to get into how we got this proof, because I want to finally go to the third part of the class, which is dynamics, since it was introduced by Alex today. Let's go there. So now I want to look at dynamics of spin glasses, and I will talk about first the case of the cubic spin glasses. So again, I'm now back on the cube, and at some point I will go back to the sphere, but let's start with the cube. All right, so I have my energy model, Hn, as before. And I want to study dynamics now. So what would be dynamics for this? So this is the Hamiltonian, and of course the energy, the Gibbs measure is of course given by exponential minus beta Hn, normalized. All right. Of course, this negative I can get rid of, and this beta I can get rid of also by just changing the beta p's, but that's the usual way to write it. So what we discussed up to now was the behavior of Zn that was given by the Parisi formula, remember? And we discussed also a little bit the properties of Gn that was given by this this whole picture that I described from Penchenko and Tarragon. All right, the fact that you could get properties of the matrix of overlaps under Gn, this limiting structure being given by the Ruel cascades and all this thing. Right? So I remind you where we have this picture, but we have very little information, in fact. We know that there is a high temperature phase where it's replica symmetric, but for the low temperature, very few cases where we can say anything. Okay, good. Then now the question is to study the dynamics. So what does dynamics mean here? I want to study a process, let me call it xt. I mean, I could call it sigma t, maybe. Okay, so this would, of course, this will be a process with values in the cube. I want it to be, let's say, a continuous time. It could be a discrete time, but here I will look at continuous time. Markov process. Markov chain, if you want. with values in sigma n. And I want it to be reversible with respect to the Gibbs measure. Okay, so I want this to be reversible, so that, of course, in the end, Gn will be an invariant measure, since I'm an irreducible, of course. So Gn will be then the unique invariant measure for this thing. So I want a Markov chain, a time evolution, which has the proper equilibrium, which will converge, in fact, of course, to this equilibrium measure. So there are many ways to do that, and any such Markov chain is kind of valid. But I need to give the jump rates. Right? I need to explain what the jump rates are. So let me call it C of sigma sigma prime. So C of sigma sigma prime is the jump rate from the spin sigma to the spin sigma prime. Okay? So, of course, I want these jump rates to be, I want C of sigma sigma prime to be 0 if sigma is not a neighbor of sigma prime. Right? So I will take a nearest, so what I'm doing here is nearest neighbor dynamics, or if I look at this on the cube, or said otherwise, it's called a single spin flip. Because what it means is that if you have a configuration of spins, the only thing you're allowed to do at any given time is spin one flip. No, flip one spin. All right? That's nearest neighbor. And then you have to choose these guys in order to be sure that it will be reversible. So for that, you need the detailed balance condition, which simply will be that Gn of sigma times C of sigma sigma prime is Gn of sigma prime, C of sigma prime sigma. Right? If you assume this, then clearly, so that's detailed balance. So you see what it means. If you weigh a vertex by its Gibbs weight, and you multiply by the rate at which you move from sigma to sigma prime, a neighbor of sigma, then this flux, if you want, should be the same as if you do it in the other direction. You weigh sigma prime, the target point, by its Gibbs weight, and then you multiply by the jump rate from sigma prime to sigma. If these two fluxes, in some sense, are the same, then the model will, of course, be reversible, and Gn will be the invariant measure. So any such thing usually are called, Glauber dynamics. And we want to study this. And then, of course, you have a choice here of those jump rates. One very usual choice, of course, you have two very classical choices that I won't study because I don't know what to say about them. One is called the heat bath, metropolis, whatever you want to choose. So this, I won't spend, these are the natural dynamics for this, and I won't spend time on them because we don't know anything about them. And that's the real open part of the subject. So typically a metropolis would do the following. You choose the jump rate as being, you look at the difference of energy between two sites, neighboring sites. So let me talk in terms of spin flip. You start from a configuration. It has a certain energy. Now you try one spin flip somewhere in the chain, okay, which means you choose one of the neighbors of sigma, and you look at the energy there. If the energy there is lower, you move. If the energy there is higher, you a priori you don't move necessarily, but you move with a small probability depending on the temperature. Okay, and depending on this energy difference. All right? That's the trick of metropolis. So these are hard dynamics that we don't know how to study. What we can study is the following. It's what are called the random hopping time dynamics. RHT. So here is the rule is very simple. In order to move from the jump rate from sigma to sigma prime is chosen to be, so there is a normalizing constant, which is 1 over n, but that's just a time scale. You can forget it. And then it's exponential plus, let me write it like this. It's 1 over Gn of sigma, of the initial point. Right? So if you want, this 1 over n is just here for convenience, and then here you have exponential plus Hn of sigma. So the important remark here is that in the random hopping time dynamics, the jump rate does not depend on the target point. This only depends on sigma. It's easy to check that it satisfies this, right? Because if you look at Gn of sigma, C of sigma, sigma prime, then here is just 1 over n. So then, of course, it's also equal to Gn of sigma prime, C of sigma prime sigma. So it satisfies detail balance, but it's very simple. Why? Because here, and it's in some sense not very natural, because it means that you move from one point, so when you are at one spin configuration, you choose one of the neighbors at random, one of the spin flips, and you move there. That's all. You don't care about the energy of the neighbor you're choosing. The only thing that you retain of this random landscape is the Gibbs weight at the point sigma. So if you are at a very large, if your Gibbs weight is large, right, then you move, this jump rate is very small. Right? Which means that you don't move much. It takes a long, long time to move. Right? So if you're at a point where the Gibbs weight is very large, which means if you're at a point where the energy is very low, if you're at a very low point, then you tend to not move much. Right? You spend a very long time there and then you move. So now you see a trap model. Right? Except it's not a trap model on the line, it's a trap model on the very large hypercube, but it's something of the same nature when you hit. So this thing plays the role of what Alex called tau. This is the tau. This Gn is tau. Right? So you wait a very long time. The mean time you wait, the time you wait, of course, is exponential because it's a Markov chain. And the mean is essentially given by the Gibbs weight, right? So by 1 over the Gibbs weight. No, by the Gibbs weight. I'm sorry. So it looks like a trap model. All right. So we will study this. And up to now, I always thought there was no. I mean, we've been trying hard to move to realistic dynamics, like the one I described before. And there was no progress. There is a recent progress to some kind of, that I will mention, of Pierre Mathieu in Marseille and Jean-Christophe Murat in Lausanne. So let me just mention it here because I think it's an important recent progress and just say in words what it is. In words, it's the following. In the simplest possible case, the case of the REM, the random energy model, which I will of course begin with, they can study a very particular case of realistic, in some sense, dynamics for which they prove results which are similar to what I will explain here. And it's kind of a specific model of dynamics. There is a simplifying feature, and also it's only for the REM. So it's not clear at all how much this could be pushed to a larger context, but that's the first time that this door has been opened, and it has been opened essentially last month. So there is something that could happen there. So watch for this team if they can push what they've been doing here. Now, I've been pushing this idea for a long time, including in a series of lectures like these ones in Marseille, which of course trying to spur the interest of people, saying that I do believe that what we've done for the random hopping time dynamics is in fact valid for reasonable dynamics, but the level of difficulty is of course much higher. Which is not to say that this was simple in the random hopping time dynamics. So let me explain now what we can prove for the random hopping time dynamics. And I will begin by the theorem, by the hard theorem in some sense. So I look at the random hopping time dynamics, which is described here, on the p-spin model. Right? So on the pure p-spin model. So everything that has been done on the pure p-spin model for the moment. And some of it can be adapted to the general mixed thing, but it hasn't been done. So let me give you, so the way I will mention this result will look very strange, and then we'll take some time to chew on on the result and make it understandable, right? But let me give you the result. So I'll take here a pure p-spin model with p larger or equal to 3. What I'm saying is not valid for p equal 2, which is Sherrington-Kirkpatrick. There is something else that I will mention later for p equal to 2. So for p larger or equal to 3, this has been proven by myself. Yeah, the order is this: Anton Bouvier and Jiří Černý, some time ago now, maybe 5 years ago, something, 4 or 5 years ago, 5 years ago. And it has been recently improved. There are a very recent version by Anton and Véronique Gérard, which gives a deeper result along the same lines. So that is probably published in 08 or 09, and this was written in 08 probably, and this is just last year. So here's the result. I fix a temperature beta, an inverse temperature beta, and I choose a gamma, a number gamma, which is between 0 and another number, which I will call, which depends on the temperature and on p, which is the minimum of beta square and beta times zeta of p. Okay? So this zeta of p is an explicit function of p, which is increasing in p. It's explicit. I don't want to write what it is, but you can compute it. It's a number depending on p. And I should not call it zeta. Zeta was something else. C of p. And C of 3 is roughly 10291. And C of infinity is, of course, square root of 2 log 2, which is the value for the rem, as we will see. Okay, so you have this number C, depending on p. And of course, now that I talked last time about the rem universality, you remember we had something of the same nature, right? We had a number, and until that number, the picture was like the rem. So I have not described yet the rem, but the result I'm going to describe now is a result of dynamic rem universality, like I described last time, for dynamics. Okay, that's what we are describing here. So here's the result now. So if I look at the clock process, yeah, so maybe I should describe a little what is happening here. When you have such a random hopping time dynamics, the jump rate depends only on the starting point, which means that in fact, this Markov chain is a time change, simply, of the simple random walk, let me call it, I don't know what, yn, on the hypercube. Right? If you forget that, so what is the dynamic? You move randomly on the hypercube. When you get to a point, you spend a time that is exponential, because it's a continuous time Markov chain, with mean given by this Gibbs weight. And then you move to a point at random around it. If you forget the time you spend, and you just look at the list of the locations you visit, it's of course simply a random walk, because every spatial movement is just chosen randomly. So this random walk is what we call the embedded random walk. It's the standard random walk, where you move in discrete time from one point to its neighbor. So the structure sigma t is simply this simple random walk on the hypercube, which is slowed down. So the picture is, you have this trajectory of a simple random walk on the hypercube, which is very different from the picture that Alex was showing of one straight line, but it's there. And it picks up, it visits this strange landscape, the random landscape, and it picks up Gibbs weights all along. Right? So, and the question is, how many jumps have you made? Right? But, or what is the time of the case jump? How much time does it take to do K jump? So I will call that Sn. N is for the dimension here. And if I look at the time of the, how much time until the case jump? That's exactly what Alex was calling delta n or something. So delta k here. So that would be what? You have to sum along this trajectory the times that you've picked up. So you have, let's say, L, you go from 0 to k minus 1. And then at the site YL, you look at the weight, the Gibbs weight. Oh, I'm sorry, I said something completely wrong here. It's not the Gibbs weight I wanted, because, yeah, of course here it's, when I write it like this, I forgot the normalization here. It's, because the Gibbs weight is the exponential minus beta divided by Zn. So if I want this, I want I'm sorry, this should be this. The Zn doesn't make any difference in my picture here. Right, that's why I had, it's this, which is, so the rate is simply exponential plus beta Hn. That's the best way to remember it. So let me write it like this, exponential plus beta h of YL. There's a 1 over n, but that plays no big role. And so that's the time you pick up at a site L, except you have to multiply this by EL, and EL will be simply an IID exponential random variables with distribution exponential of mean 1. Right? So this is now an exponential, this whole thing is an exponential random variable with mean this. All right? So that's the time of the case jump. All right, so that's, and then of course I can do like Alex explained, I can look at this, define this, interpolate in time if you want, and define for any t, I can look at this as being Sn of integer part of t. Right? I will just define this. So my sigma of t now is simply yn when, so what does that mean? That means I've done n jumps. Right? So it means that the time of the n jumps is between, now I have to be careful, is it n or n minus 1? Right. So this tells you that this random walk is, this Markov chain is simply this random walk with a time change. And the time change is measured by this guy. So we call this Sn of t, we call that the clock process. It's simply a clock. So the dynamics is simple. It's a random walk on the cube, and it carries a very strange clock. And every time the clock rings, it moves. And this clock, of course, is simply you accrue those numbers, you add those numbers along the trajectory. All right? So, you know, in this trivial model that Alex was explaining, what he said was that the clock process, properly normalized, converges what he called delta. When you normalize it properly, and he explained this Poisson point process and the arc-sine law and all that, converges to an alpha-stable subordinator. So what is an alpha-stable subordinator? He gave the law, but it's simply a process in continuous time with independent increments, which is always non-decreasing. That's a subordinator, means non-decreasing. As this thing is, of course, non-decreasing, it keeps increasing because you add positive numbers. And in fact, whose distribution of one increment is a stable law. All right? So the result here is, in words, and I will take quite a while to explain this, is the clock process in a time scale, in time scales T of n equal, so I have to be clear here, something like exponential n c of gamma, not c. That's why there was a zeta there. I don't know. D of gamma converges to a stable subordinator. When properly normalized, so let's say V alpha, and this alpha is a function, is an alpha of gamma. So this should be, we'll take time to explain this, but this should come as a surprise. It says, what Alex has explained in this very simple model when you move along a line and you never even come back. So the underlying random walk, the model in Alex was similar, except the underlying random walk over there was not a random walk at all. It was, you were start from 0, you go to 1, you go to 2, you go to 3, purely directed thing. Here, everything's different. We have the underlying thing is a random walk on a cube. There is no drift here, no bias, no preferred direction. It's really a random walk on a very high dimensional object. Second, so that's the first difference. And still the result is the same. Second, in the case of, Alex explained, the weights, the taus, this would be the tau. I could call that tau of YL, and then it would be the same thing. The taus were IID random variables. Right? They were independent. And that's this independence that you see in the fact that the limit thing is a subordinator, which has independent increments. Because of course, what are the increment of this? If you look at Sn of k minus Sn of L, you will find a sum of these guys. If these guys are independent, then the increments are independent. So that was the origin of the fact that the limit is a subordinator. When you say the limit is a subordinator, you say the increments are independent. But here, the increments are far from being independent. These guys are essentially the Gibbs weights. They are extremely correlated. Right? So we have very correlated variable, and in the limit, this correlation disappears. So already two very big differences. The random walk is way more complicated. Second, the weights, the taus, are very correlated. Now comes the third difference, which is in fact the most surprising thing. In the model like Alex described it, the tails were heavy for the taus. And they were heavy tails with an exponent alpha. So you put the heavy tail in it, and of course you find that the limit is stable with exponent alpha, the same alpha. So you have this machine. At the beginning you put a trivial random walk, you put independence, and you put heavy tails. And in the end you get, of course, independence of increments, that's a subordinator, and of course stable subordinator because you had heavy tails. Here the random walk is complicated, the thing is not independent, but the worst thing is that there is no heavy tail at all here. So the first thing is to explain, even before I explain anything about the normalization, here there are many things I have to explain. What is this time scale? And what does converge mean? In what sense? There are many different senses. And so in fact the difference between this work and this work is the nature of the convergence that I will explain. But before explaining anything is where are the heavy tails in this model, right? You may believe that the correlation disappeared, but where are the heavy tails? And look at the result. I said that there is an alpha, but the alpha, it's not a machine in which I put the alpha and I get the alpha in the end. The alpha is produced by the model. And what is really interesting is that in fact, for each time, so you look at a time scale which is exponential n times a constant. Right? This constant or this gamma is essentially in one-to-one correspondence. And then you find, so for these very long time scales, you find an alpha which depends on the time scale. Right? So here, the tail, the alpha, depends on the time scales. The exponent. So you have an exponential Cn, and then you have an alpha which depends on C. Right? It will be between 0 and 1, but the heavy tail moves along. Right? So that's a strange thing. So just to be sure that you are with me, if I take this time scale very short, I mean, if the d of gamma is close to 0, what would be alpha? And if this time scale is very long, what would be alpha? Alpha is between 0 and 1. So at the two ends of the regime here of the range, it should be 0 and 1. Okay, I'll let you think about that. You know, you have one. It's a spin flip. It's either 0, 1 or 1, 0. I mean, you have to think. But, all right, so where is this alpha coming from? So let me explain that. So maybe okay, here is the idea. I look at this time scale, at this variable, this tau, right? So I look at what is the probability that tau is larger than, so that's this Gibbs weight. Let's say that, okay, maybe I'll do that later. Let me also keep this mystery for a while. Just want to insist on that. But now I want to state the theorem properly. So, because I have, in fact, it's better if I give you what the alpha is. So the alpha is, in fact, here, simply gamma over beta square. All right, in fact, it converges, there's also a normalization constant here. It converges to, so let me state the theorem properly. So the normalization is this now. I look at exponential minus gamma n. My clock process at time t, n to the 1/2, exponential n, gamma square over 2 beta square. That's the right normalization. This converges in distribution. This converges, I'll say how, to alpha stable subordinator. With here you have a constant. So this constant kappa is a function of gamma, beta, and p, and it's explicit constant I don't want to put there, and alpha is gamma over beta square. All right, so that's the theorem. So let's look at what this means. Forget this square root of n for the moment. So this says I'm taking a time scale of this order, exponential n times this constant. And in this time scale, that's not a time scale, the number of jump. Right? So this is the time scale. If I look at it at the time scale exponential minus gamma n, okay, this is the time it takes to do this number of jumps, essentially. So the time it takes to do this number of jumps is essentially this, exponential gamma n, multiplied by something random, which is this stable subordinator. Okay? So that proves what Alex was saying, that is this trivial model that he was describing, in fact, can carry information in, much, much more complicated things. So the definition of convergence here, so this is a process, so I can look at it as a process in T. So the convergence is in the space of the, let's say D0T with values in R plus. So the space of Cadillac functions, and it's with respect to what is called the M1 topology. So I don't want to spend too much time on this. And it cannot be improved to, so let me explain this just with words. The space D is simply the space of function with jumps. And on this space, there is a natural topology. In fact, there are natural topologies. And they are all called Courant topology because Courant introduced them. And the one that is usually used is called the J1. I mean, when people say Courant topology, they mean J1 topology. I don't want to say too much about this, but the convergence in the J1 topology is not true here for this thing. But it's true in the M1 topology, which is a variant of the topology, and that's what it is. And in fact, in the paper by Bouvier and Gérard, they improved that. They introduced some kind of block clock process for which the convergence is in the J1 topology, which is a stronger result. So the convergence is in the M1 topology, but I didn't say under what randomness here. So this defines a random function in this space D0T, and it converges, its distribution converges to the distribution of an alpha stable subordinator. But under what kind of thing? So what is true is that it's valid under, because we have two levels of randomness here. One is the randomness of the landscape, the Gibbs measure, the Hn, the random environment, and the other is the randomness of the random walk. The random walk moves around. So you pick the trajectory of a random walk, and you pick first and you pick the environment. So you have two randomness. So what we proved with Anton and Jiří some 5 years ago was that if you fix the trajectory of the random walk, almost surely in the trajectory of the random walk, then you had convergence in distribution. Right? Then, of course, you can integrate the random walk, and so, of course, you would have convergence in distribution under the Bose randomness. What Anton Bouvier and Véronique Gérard proved is much better and much more natural. They proved that if you fix the environment, almost surely in the environment, then you have convergence. Right? And that's a much more natural result. In the end, so they proved the quenched version. What we proved was a strange result which implied an annealed version. Right? Because who cares about fixing the trajectory of the random walk? So we proved something which implied the annealed version, they proved the quenched version. That is, fix the environment, fix the randomness of the Hn, and look at this process, it converges in distribution to this. So they proved this value for p larger than 5, and for p equal 3 and 4, they have, instead of having an almost sure in the environment, they have something in probability in the environment, something a little weaker. All right, so that's the result. So let me explain. So let me give a consequence, which is not a direct consequence, but kind of, which should now be familiar, which is aging for these things, as Alex described it. So let me look at the following function. I look at the probability, I look at 2 times, and a small epsilon. I look at this quantity. This would be the probability that the overlap of my sigma of t and sigma of t plus s is, I should write my time scale, exponential gamma n. Oh, by the way, here I should then just put gamma, and that would work. And sigma of t plus s gamma n, exponential gamma n. The probability that this overlap is larger than 1 minus epsilon. So what is this? Right, this is the overlap. I could put an n here if I want. So what is this? Remember, the overlap is 1 when the 2 points are the same. So this looks like what Alex was describing is what is the probability that this random walk he had was at the same point, right? And this was aging at 2 different times. Here we're not looking at that because it's asking for too much on the cube. We're asking at the fact that they are close. We're looking at the position of the dynamics in the time scale exponential gamma n at the time t, and at a later time, t plus s in the same time scale. And I'm looking at the fact that this overlap is very large, it's close to 1. So this means that the distance is small, right? So I'm asking what is the probability that that the dynamics at 2 different times in this time scale are essentially at the same point. And the result is, oh, and by the way, when Alex said that aging is essentially looking at the probability that 2 things are at the same position, that's not the way physicists think of it. What physicists think of this, aging, is thinking in what they call the 2-time plane. That is looking at 2 times. That's the real thing. But the observable you choose depends on the dynamics. For instance, if you look on the sphere, it's completely different. So when you think of Markov chains, we tend to think of Markov chains that converge quickly to their equilibrium measure. And then we tend to say things quickly. So if you take the Markov chain at 2 different times, the only important thing is the difference between the times. And it should be like a function of the difference. So the only thing that would be important in this should be S, when you have a nice convergence. But thinking in the 2-time plane, as the physicists say, is to think that this function will not be only a function of S. This here will be called the age of the system. So look at it. You have your system, you let it evolve until time t, which will be very large. And then you observe it between the time S. So this is the size of the time window, the size of the time window of observation. So you have your model. It's old, it has age t, and then you observe it for a time S. For simple systems, it's only S that is important. For interesting system, the age plays a role. The older the system is, then you feel the age. So this is, we choose in this case this observable, and what we find is that this thing converges to guess the same function that I call f alpha of t over t plus s. That was A in Alex's thing, and this was B. So this is A over B, and this f alpha is the same function. F alpha of u is sine alpha pi divided by pi. Integral from 0 to u of v. So I should this time not make the same mistake. From 0 to u. Here. of v to the alpha minus 1, 1 minus v to the negative alpha dv. That's the same arc sine law. That's what Alex called arc sine. All right, so you see we get the same thing. So let's look at what this tells you. This says the probability for the system in this time scale to essentially be at the same place after an evolution of length s does not depend on s only, but depends here, as you can see, on s divided by t, right? Because I can, of course, divide all this by t, and I get 1 plus 1 over s over t, right? So the important variable here, this is a function of, forget the function, but it's a function of s over t. So what is s over t? That's the relative age, the relative duration. The window is of length s, but that's not important. What's important is the length of this window when you divide it by the age, t. So this means that in order for this probability to be significant, you need s to be of the same order than t. Right? Which means to begin forgetting your past. So when your system is old, in order for it to significantly forget its past, not stay at the same place essentially, then you have to wait for a time which is proportional to the age. And that's aging. So this means the older the system is, the slower it is. The system moves, but slower and slower and slower. And this describes precisely how it does it. So what is the strength of all this? This is very universal. The picture, as you've seen with Alex, can be done. And we will see something of the same type in random walk on trees and percolation clusters, which in fact is due to the same trapping mechanism. And so this theorem says that in the sense that I just mentioned. But you see we have time scales. So let's look back at what the theorem says. The theorem says this universal picture of trapping is valid in time scales which are very long, exponential in n. Why do you need such long time scales? It's because it's so let me say that again. The tau here, the time you spend in a trap, is essentially exponential beta h. But remember that the extreme values of h are of order n. Right? So the natural time scales, in fact, the time it takes to get out of one of these deep traps is of order exponential n. Right? So that's why you need this type of thing here. So you have deep traps, so the time to get out of them is exponential n times a constant. So here we're looking at these exponential n times a constant, which is, if this constant could be as large as we wanted, this is essentially also the mixing time. The mixing time has been studied, the time it takes for these random walks to reach equilibrium. But what we see here is not at equilibrium. For a very good reason. What we see here is completely model independent. We see no p. The model here is given by p, and we see no p. P is, of course, hidden somewhere in this constant, but that's all. There's no p here. So what we see here is totally universal for p equal 3, 4, 5, 27. It's the same model. It cannot be true when you get to equilibrium, because at equilibrium you feel the value of p. You feel the model. Right? And so this phase here is purely transient. It's very long time scale, but we are still far from equilibrium. And this phase far from equilibrium is universal. That's what it says. Now, why do I say that we are far from equilibrium? It's this condition, which I pulled under the rug, of course. Gamma has to be smaller than something where you have a p. You have the temperature, but you have p. So this means this time scale in which this is true, this is valid until a certain time scale, and then it breaks. Then it becomes p, the universality breaks. Okay? What happens later, we don't know. This is an open problem. gamma larger than this minimum of beta square and beta C of p. Right? You can't expect the REM picture to be always true. So something else will happen, and you should see, if it is true, that we have a one-step replica symmetry breaking and then a full replica symmetry breaking. You should see a phase in which we have something else than REM, something closer to GREM. You should see something like dynamics on a Ruel cascade with two levels. Right? What we see here is something that you could build as a Ruel cascade, as dynamics on a Ruel cascade with one level, depending if you count the root or not. Okay? So something else should happen there. And then if there is really, like Gardner predicts it, a region of temperature where you have full replica symmetry breaking, then all hell breaks loose, and I don't know what will happen, but it will not be it will be like dynamics on an infinite Ruel cascade. So this, of course, is still completely open. All right, so how do I describe this now in terms of what's happening? So instead of proving this theorem, let me explain it. And the proof is pretty serious. So I will explain this maybe by, okay, before doing that. So yeah, let me explain this first in the case of, so now I'll back down. Instead of doing it in the p-spin model, which is hard, I will simplify it. So let me explain what's happening first in the complete graph. Right? So, or maybe I will first explain what happens in the REM. So first, the case of the REM. Okay, so now I look at the dynamics for the REM. So I have the same thing, the same picture, except my Hn now are simply IID. And the REM is supposed to be the limit of the p-spin when p tends to infinity. So we should have exactly the same picture, but with C of infinity here, which is square root of 2 log 2. And the rest should be the same. So how do I, so my tau now, my tau of sigma is exponential beta h of sigma, hn of sigma, and now these guys are just IID n01 because it's a REM. So the simplification I have now is that my taus are independent. So it's very similar. I simplify one thing back to the model of Alex. There are two things that are not yet simplified, that the underlying random walk is still complicated here, and this thing have no heavy tail. So let me explain on this one why we have heavy tails. So let me explain the appearance, in this case, of the appearance of the alpha. So let's do the following computation. What is the probability that this tau is larger than exponential alpha beta square n multiplied by a number u, knowing that tau is larger than exponential alpha beta square n? Right? So let's look at this computation. I look at all the traps that are deeper than this, that are in this scale, right? Which means essentially I'm looking at the points where the h are below this level. And among those, I want to look at the probability to have a depth which is, say, 17 times larger. Right? But I ignore the smaller traps. I just condition on having already deep traps. So this computation is, of course, trivial in the case where everything is in this case, I mean in the case of a Gaussian variable, because this is of course the same as the probability, this tau is exponential beta h, it's the same as the probability that beta h, this is, if I want this to be n0, there are n0n. So let me put n01 and then have square root of n. Then beta h square root of n larger than log u. So log of this larger than log of that, which is log u plus alpha beta square n, conditioned by h larger than alpha beta square n, square root of n h. Right? That's the same thing. I just took the log of this. All right. This, of course, is simply the ratio of the probability that h, of course, this means h of sigma, larger than 1 over beta square root of n log u plus this divided by the probability that h is larger than the same thing without the u. Now, h being a Gaussian variable, you know the tail. So the tail is roughly exponential minus 1/2 of this thing square. So it's 1 over beta square n, and then you have log u plus alpha beta square n square, and you divide by, so you exponential plus 1/2 of 1 over 2 beta square n and alpha beta square n square, if I'm not mistaken. All right, so you compute this. Obviously, you expand this square, and then this guy disappears with this guy, because you have a minus sign here and a plus here. This square will be very small, and the only thing that remains, this is just algebra, is the double product of these two guys, is the product of these two guys. And so the product is exponential minus 1/2, 1 over beta square n, this term, and then you have 2 times log u times alpha beta square n. Right? So let me say again what's happening here. You expand this square, you have this term square, which is the same as this one, so it disappears. Then you have the cross product, which is here. And then you have this one square, which will be much smaller because there is no n. So let's forget the other term. Now you compute this, the beta square disappears with this beta square, n disappears with n, 2 disappears with this 2, and you get exponential minus alpha log u, which is just, lo and behold, 1 over u to the alpha. So here's where the heavy tail is. This thing is of order, when n is large, like 1 over u to the alpha. That's the basic computation. So again, this says the following. When you have random variables that are Gaussian, exponential of Gaussian are not heavy tails. So my taus are not heavy. This is not heavy tail. If this is a Gaussian, this has moments of all orders. But if you restrict yourself to the taus that are larger than this, what you see is like a heavy tail. So if you look at a window, which is exponential alpha constant time n, and you move this alpha, in these different windows you see, in fact, something which looks very much like a heavy tail. But depending on this alpha, you have a different alpha here. This explains why in different time scales you have different subordinators. All right, so that's one thing to explain the alpha. And now let's look at what happens to the REM. So, or maybe I should just explain what happens for the p-spin in general, but okay, let's look at what happens to the REM. I say that in words. So in the time scale, so now I'm talking about the REM, and then things will be simpler. In the time scale exponential alpha beta square n minus alpha over 2, this is subdominant. So I look at this time scale. So my gamma is alpha beta square, if you want, here. Remember, gamma is alpha beta square, because remember that I want to choose here my gamma to be okay, I didn't write it, but alpha is gamma over beta square in my theorem. So this is the right choice. So in this time scale, the process makes exponential alpha square, beta square, n over 2 steps. Okay. So in a time scale like exponential Cn, it makes a certain exponential dn steps. And it explores, so this you can write as, I will write it as 2 to the rho n. Right? And so rho, if you look at this, rho is simply alpha square beta square over 2 and log 2, because here I put the power 2 and here I had e. Rho is this, right? So in fact, it means that the process explores 2 to the rho n sites. So it's as if, so it's like a REM at equilibrium, but for little n now, which is rho n. We're exploring, much less sites than there are. So remember what I explained last time was what I call the resampling thing. Imagine that these 2 to the rho n site, I called this m last time. So I'm looking, the process chooses 2 to the m sites, and m is smaller than n, rho n. In what I explained last time, I explained what would happen if you chose those 2 to the m sites completely randomly. I said take a site percolation cluster, a Bernoulli cloud, right? And then I said, even if you have correlation between these things, like we have in a p-spin, the correlation would disappear, right? So here is a phenomenon of the same nature, except that this cloud of points that we have chosen is not chosen purely randomly. It's in fact the trajectory of a random walk. These points. They are not IID, they are not, that's the path of a random walk, right? So then the question is, why is it that the path of a random walk could be looked at something like an IID cloud? Right? It doesn't look at all like points chosen purely randomly. So there is something here which is absolutely specific to the fact that we're in high dimension. In large dimension here, on the cube, when you take the random walk, it's something, you have to understand the potential theory of the random walk to do all this on the cube. How does a random walk visit, a standard random walk visit the cube? And what happens on the cube, and is very well known, is that after very few steps, a random walk completely forgets its past. It's lost entropically. So it's easy to understand this. If you are on the cube, how many neighbors do you have at distance 1? N. How many neighbors do you have at distance 2? N squared. How many neighbors do you have at distance n, at distance k, with k not too large? Essentially n to the k. Right? So it increases, so the volume of the ball increases, of course, exponentially, at least initially, with the distance. So when you've made k steps, you have so many points that you can explore, right? An exponential number in the number of steps. That is very difficult for you to come back to where you started, to remember where you started. Very quickly, you totally forget this. And this is, in fact, put quantitatively on the following, with the following statement. If you take a random walk, the standard random walk on the hypercube, you have what Percy Diaconis and David Aldous introduced as the cutoff phenomenon. As long as you haven't made 1/4 of n log n steps, essentially your position is very correlated to where you started. You're very close. After 1/4 of n log n steps, you're totally lost. It's as if you were choosing the point at random. So this means the following. In my trajectory here, of the random walk, I have a lot of points, 2 to the rho n, an exponential number of points. Now, if I sample along this trajectory every n log n points, I will still essentially have the same number of points. I will miss a few. But these points will be essentially as if I'd taken them at random. Because the random walk forgets very, very quickly any correlation with its path. So it's not unreasonable to think that what I explained with this random cloud could also be true here. And this is, of course, what guided our intuition. And it is true. So let me go on. And then once you have, it visits this number of points, so it's like a REM with this thing, or if you want, it's like a REM with an effective temperature, a different temperature. That's the way physicists think about it. An effective temperature which is different, which is, in fact, let me call it beta rho, which will be beta divided by square root of rho. Right? Because look at the model. The model is this, beta h square root of n. If you replace this n by n rho, then you have a square root of rho. Right? Formally. So it changes the temperature. Rho here is smaller than 1. So 1 over square root of rho is larger than 1. So this beta rho is larger than beta. And so, and of course, this 2 to the rho n is a small fraction of my 2 to the n. So the system is really out of equilibrium. And this condition I'm saying here says that this rho is small enough. All right, and then look now along those paths, along this trajectory of the random walk with 2 to the rho n steps. The question is, what is the minimum energy observed? Or Hamiltonian, if you want. So you have this trajectory, and the question is, how deep do you go? So I'm asking exactly the question that Alex was asking along the line. Right? You look at these deep traps. What is the deepest one you can find? So of course, in the case of the REM, it's simple. Right? In the case of the REM, this is simple because we have IID random variable, and I told you, now we have a collection of IID random variables, and Gaussian, we know their minima, right? And so it's of order, the order of magnitude is, of course, square root, remember what it was? Square root of 2 log 2 times n, little n, but little n is now rho n. So it's square root of 2 rho n log 2. Okay? So the mean waiting time so the mean waiting time, the tau if you want, the maximal one for this extreme trap, right? For this deepest trap along, let's write it like this deepest trap along the path. So you have this path, you look at the deepest hole, and the time you spend in it, of course, is simply exponential of this. So it's exponential beta square root n times this. And the order of magnitude is square root of 2 rho n log 2. So this is exponential beta n. You have square root n. And then you have the square root of 2 rho log 2. Right? Which is, of course, the same as my effective temperature, beta rho n square root of 2 log 2. Right? All right, and so this is, of course, also what I call exponential alpha beta square n. If you remember what rho was, because remember rho is this. So 2 log 2 times rho is alpha square beta square. When you take the root is alpha beta, and then you get this. All right. So this tells me that the time, in this time scale, I have this path. The deepest trap will keep me exactly the same order of magnitude at the time I had chosen. The time scale is fixed by the deepest trap. But now you have to ask yourself the question, why is the deepest trap, the time you spend in the deepest trap, the same order of the total time? Right? That's not clear. You needed, I mean, in the case of Alex, you needed this alpha. The fact that we had beta rho, my effective temperature, larger than beta critical, and that's the condition on rho that is over there, means in fact that my alpha is smaller than 1, and means that the total time spent by the trajectory is of the same order as the largest one. So let me remind you that I explained that. If you take IID random variable with heavy tails, and alpha is smaller than 1, I explained some time ago that the maximum and the sum are of the same order. Right? This is, of course, only true if alpha is smaller than 1. So the condition we have here, which is the same as this condition for physicists, that is, you are at low temperature. The effective temperature is larger than beta critical, means you are at low temperature. This means also that alpha is smaller than 1. Then this tells you that the total sum, that the sum is the same order than the maximum. So the total sum is of this order. Right? It also tells you, if you believe this picture, what I said before, that is, the sum should behave, when you have a heavy tail, the sum should behave like a stable subordinator. Right? So for the REM, now we have everything we need. Of course, you have to prove it. We have independent variable, which are not heavy tail, but kind of, because of what I've written over there. The ones that are relevant, the ones that are in the right depth, behave like heavy tail. So you have independent, kind of heavy tail. The problem, of course, and then, so the sum should be like a stable subordinator. If you believe that the random walk, really mixes sufficiently well. Now, the picture is different for the p-spin model. For the p-spin model, you have to understand, so this would still be true, but you have to understand many things. First, when I said the order of magnitude of the minimum energy, this is not trivial, because now you have this path of the random walk on the cube, and you're looking at the landscape of energy along this path, but the landscape of energy is now very correlated. So you have a bunch of correlated Gaussian variables, and you want to understand their minima. This is difficult. And you have to prove that, in fact, this minima is as if they were independent. And of course, they are not independent, because now along a random walk, points that are close by are very correlated. So you need to do some renormalization here. You need to block things together. This is a little difficult, but it's still true. And of course, this is the hard part, to understand this. And then to understand that it converges to the subordinator, you need to prove some real independence. So where is the independence coming from? Is along the trajectory of this random walk, you will sometimes hit here a deep trap. The points around it will be deep too, and very correlated. So you cannot simply take the time you spend in one point. You have to take the time you spent in points nearby this point. All right, after a while, you get out of this region, travel in the cube, forget completely where you come from. You reinitiate at 0 if you want, in the bulk, and then you find another such thing. But you expect that this other such thing will be far enough from this one so that the correlation will be close to 0. And so in a coarse-grained picture, you have one region here, one region here, one region here. They are independent, and so it behaves like a REM. Now you have to understand what's happening inside each of these regions. This is really delicate, right? Because in this region, we're in high dimension, things are correlated very seriously. You have to understand that, right? But what you can prove is that in some sense, this one-dimensional picture that Alex was saying is essentially true. around the minimum, around a deep minimum here, the trajectory of the random walk will essentially locally zoom like a ray, just never come back. So essentially, it's like a one-dimensional structure in this hypercube, locally. Of course, globally, it's certainly not like that. But locally, it's like that. Then you're back to studying now the extreme values of a Gaussian process in dimension 1 along this ray, very correlated. There, you cannot miss the correlation. But when you study processes in dimension 1, then you have tools. That is what is done there. So very briefly, this is how we do this with Anton and Jiří. What the real plus that has been brought by Anton Bouvier and Véronique Gérard is something that Véronique has remarked before, and she studied it first in the REM. She's brought, in fact, a technique which relies on a very classical result about sums of IID random variable due to Durrett and Resnick, which here is deeper than what I just said, but is exactly the right tool to do it in this better quench version than the annealed version I was explaining before. So with this, so could you answer the question about whether alpha was 0 or 1 or? So when you go to short time scales, but in fact I gave you the answer. When you let this gamma go to 0, when you are time scale which are very short, alpha goes to 0. When gamma goes to the other end, alpha goes to 1. So let's think of what this means. If you take very short exponential time scales, so they are long because they're exponential, but on the short end, then alpha goes to 0. So what does that mean? If you remember what I was saying about the sum and the maximum, or if you want to remember, if you take the ratio of the maximum by the sum, this goes to, if you take the ratio of the maximum to the sum, the time you spend in the deepest trap, you divide by the total time. And then you take the time you spend in the second deepest trap and you divide by the total time. And the third, and you divide by the total time. So the proportion of the time you spend in the deepest, second deepest, third deepest. This has a name, which is student Vladas. It's of course the Poisson-Dirichlet process, right? Which I described before. So we are back with this guy. So when alpha goes to 0 in short time scale, essentially the minimum is taking a larger and larger and larger proportion of the sum. And in the end, when alpha is 0, of course, there is no 0 stable subordinator. Then it means that the maximum is really the sum. You spend your whole time in one trap. Right? So how is that possible here? It means the following. If I look at time scales which are barely exponential, my system begins to move and finds a deep trap and doesn't have enough time to get out and find another one which is of the same order, when alpha is really tending to 0. So on the contrary, when you take time scales which are long enough and if you come closer to equilibration, then, for the REM at least, then you have enough time to find a deep trap and then enough time to equilibrate along many, many more of traps of the same order of magnitude. Right? That's so when alpha is close to 0, the dynamics are kind of stupid. You move around, you find a trap, you fall there, and you stay there. Right? So this phenomenon I will describe next time, because if you now take, so this is now the next result, and so the case alpha equals 0 in some sense, which means the following. You take sub-exponential time scales. What happens if you look at a time scale which is exponential little o of n, right? Which is, of course, most of the time scales. Real life time scales are exponential little o of n, seriously. So what happens then? Then we can prove for any p larger than 2. Now, this contains the Sherrington-Kirkpatrick case. So in those time scales, this is a result by Honor Gun and myself, which has been also improved recently by Anton Bouvier, Véronique Gérard, and I'm sorry for that, a younger student in Berlin whose name escapes me. And the result now should be, if you believe that, the clock process should converge to a zero stable subordinator. Right? Because this corresponds to alpha equals 0. But the zero stable subordinator does not exist. There is no way. So you can't really, and in fact you cannot normalize. So if you take a sum of IID random variable with very heavy tail, what does alpha equals 0 correspond to? It means that your tail is even heavier than any polynomial, right? Inverse polynomial. So say the tail is like 1 over log u. Then you have no way to normalize this linearly, that is divide by something, so that it converges. The way to normalize is nonlinear, and it's called for IID random variable, it has been known for a while. And it converges to what is called an extremal process. And I'll explain next time how this is true here. And we gave that a name with honor, and we call this extremal aging. The nice part of this is that this extremal aging is completely universal. It includes p equal 2. That's the first result in the dynamics of the true SK model. So what this tells you is that if you take the true SK model, and remember for physicists there's a big difference between p equal 2 and p equal 3, then the dynamics in those short time scales are completely the same for everything, for 2, 3, REM, and as I said, in fact, they are the same also for Edwards-Anderson. So these dynamics in transient regimes are all the same. You see all the same thing. A kind of stupid thing, that is, you have the time to find, even if the time scale is pretty long, it could be exponential square root of n. You have the time to find, or exponential into the 3/4. You have the time to find one deep trap, and you stay there, right? And so that's why I was saying that, if you do simulations of spin glasses by nearest neighbor things, you're in trouble. Because whatever your model, you will end up doing this. And of course, all the models will be the same, right? And because you have no way to simulate for exponential constant n. So you will simulate for exponential little o of n, and everything will be, you forget totally the model. Everything is the same. And that's not the right way to infer anything serious about the models. Because you're so far from the Gibbs measure, then all the models are the same. Right? Happily, there are methods to simulate spin glasses that are not nearest neighbor, and so that are supposed to converge much faster. All right, and so next time we're going to deeper things here.